Hello, I'm Mike Baran from Johnson Matthey. My co-author, which is not listed on the program, is Bart DeGraff from Intercat, which is a Johnson Matthey company that does additives for the FCC process. So the first piece of the NOx control area is for reciprocating internal combustion engines. They're used extensively in the oil and gas industry, from the very beginning in drilling through transmission of gas. So we see NOx control requirements throughout the process. And some NOx control requirements have slipped through the cracks because of some issues with implementing SCR. So engine uses in oil and gas, this is just a little list. there's many more. Compression at the wellhead and downstream, transmission along the pipeline, typically gas. Power generation, quite a bit of drilling rigs are electrified. So you have power generation engines on the rig that then feed power to the rig itself, lights, air conditioning, the drilling operation, fishing. They lose pieces down the hole and they got to find them. And pumping. So we know fracking. There's also acidizing, where they pump down acids and they dissolve certain components to open up the structure to allow the gas to flow. And then cementing, where they pump down cement to do an outer case for the casing when they drop it in. Also, you have loosely tied to oil and gas industry is power or CHP using biogas or landfill gas. Bill talked about that a little bit on combustion turbines. That's a very, very big thing in engines nowadays. We're seeing a lot of biogas and landfill gas opportunities. And as he said, it is a very big challenge to get that siloxane number down. And typically you want to see that below 5 ppb, which is the detection limit of siloxanes, at least at a couple labs. So the general arrangement of an engine SCR kind of looks like this. You may incorporate, if it's a diesel engine, you might incorporate a diesel particulate filter upstream. You may incorporate an oxidation catalyst upstream. You then go into the injection site where you typically inject urea, but you can inject aqueous ammonia or anhydrous ammonia. Those aren't as easy to permit, so typically we see urea. It then goes through the mixing duct where the urea changes into ammonia, and ammonia then reacts over the SCR catalyst to reduce NOx. In lean burn engines, unfortunately, we can't put a three-way catalyst on because the excess oxygen will not allow the NOx reaction to occur as it would in a rich burn engine or your gasoline engine in your car. I'm not really going to go through this, especially since this area here got messed up. But I think Bill went through the reactions quite readily. Here's a little bit more detail when you look at the presentation of the process by which the SCR reaction proceeds. So there's a lot of different diffusions and reactions on sites. But I think we went through the reaction kinetics and principles pretty well in Bill's talk. So the potential SCR challenges in drilling, there are rapid load changes, as you can imagine, on engines, even if they're providing power to the drilling. They may hit bedrock, they may hit something soft, and you may see very big load swings on a short period of time. So with those load swings come NOx swings. And if you rely on things like chemiluminescence systems or SEMS or something like that, there's no way to capture that because as you'll see in one of the case studies, the load map looks like an EKG. It's a very extreme load swing. And there can be some extreme environmental conditions. So typically, I'm talking about land-based stuff, but you could be out in the middle of the ocean, you could be up in Alaska, you could be in Wyoming at negative 40 degrees Fahrenheit. So there are some environmental conditions that are challenging to make sure that everything works well. The gas doesn't cool down below the temperature you can inject. You don't freeze the urea. So there's a lot of potential SCR challenges there. And in compression and transmission, we tend to see a lot of older, slow speed engines. The SCR requires a certain temperature to inject urea, and quite a bit of those older engines, slow speed, don't get up to that temperature for very long. So the options are put in a burner or use aqueous or anhydrous ammonia, which the last two aren't really that attractive to people, and the burner isn't that attractive to the operators. And it represents a change in the operator or owner mindset. Typically, these transmission engines have been exempt from SCR requirements. So any NOx coming out of those engines just is not controlled. So here's case study number one, gas drilling. You can see the EKG down there at the bottom. This is a natural gas drilling rig running with diesel engines. So we have a system in Wyoming. Each rig has 3 engines. Each rig uses 2 engines at a time, load sharing. And they used low sulfur diesel for a while. They're now on ultra low sulfur diesel. But you can see the challenge of following that load curve, and with each load spike, you get a NOx spike. You have higher flow, exhaust flow, you generally have a different concentration of NOx. So very challenging, but it can be done by being having a more responsive control system and mapping the engines such that you can determine at each load what NOx level you are at and what urea injection you require. Gas compression. So here in gas compression, sometimes we run into another problem. The engines are very, very efficient, but they are very, very hot. The exhaust coming out of these 3616s were above the SCR temperature that we list as the maximum. So in this case, we actually incorporated tempering air blowers prior to the SCR housing so that we could, actually that's the other way around, that's the oxidation, that's the SCR. We put tempering air systems in to cool down the temperature so that the SCR reaction could proceed in a robust manner. Recent developments have largely reduced the need for that. we can now run at higher temperatures due to different technology that we've adapted from on-road SCR systems. And we talked about biogas and natural gas. So biogas, this is Orange County Sanitation District, South Coast Air Quality Management District passed a rule that these wastewater systems cannot emit more than 11 ppm of NOx. And the rolling average, I believe now, is 24 hours. But the interesting part of this is they use biogas, they clean it up, then there's a polishing tank. We talked about sampling gas for siloxanes. They actually sample between the main tank and the polishing tank. When they see breakthrough of siloxanes, they know it's time to do something. This helps prohibit the siloxanes to go through the catalyst and kill it. In here we have oxidation catalyst and SCR catalyst, both of which make great glass on the surface if siloxanes go through. They actually purposefully turned off the system and ran it through the oxidation catalyst just for fun, to make sure that they weren't being sold a bill of goods that siloxanes were bad. It died within 2 days. And the concentration wasn't very high either, so it doesn't take long. So SCR is a very mature technology. There are new developments, especially on the engine side, that have been made recently that allow for higher temperature operation, lower ammonia slip, higher efficiency with a smaller footprint. So there's still a lot going on in an industry that seemed to stagnate on the engine side for 20 years. There are some challenges to implement the SCR in the oil and gas sector. Many can be overcome, but we got to work with the operators and see what makes sense. And SCR systems are currently installed and operating on a variety of RICE applications for drilling, compression, power generation. So we do see quite a bit of SCR in the oil and gas industry, but there is a good portion of the oil and gas industry that doesn't require it. Like I said, transmission engines typically you don't see SCR systems on. So now I went from the gathering side, now I'm going to move into FCC. So fluid catalytic cracking is a methodology by which oil, petroleum is converted to gasoline and other byproducts. It turns out that the major process is not the big problem. It's the regenerator of the catalyst that's used that's the big NOx emitter. So you have the main reaction chamber where you have hot catalyst and you put the oil petroleum product over it, and you make gasoline and other byproducts. You also coke that catalyst up with various components. You then move the catalyst to the regenerator, and every regenerator is different in the way it's designed, how much oxygen, where you introduce the oxygen, how well it flows around. But that really affects the amount of NOx and hydrogen cyanide that are developed as part of that regeneration cycle. So the FCC feed contains contaminants in the coke. So you have sulfur, nitrogen, metals, various things. Nitrogen and coke combust to hydrogen cyanide. Not a great actor, but it's not NOx, but I don't really want to breathe it. Ammonia, nitrogen, and then NOx of various sorts, NO, NO2, N2O. So depending on the conditions in the regenerator and the CO promoter that you may use in the catalyst, you can get various byproducts, one of which is NOx. So NOx formation in regenerators are generally increased by high excess oxygen levels, poor coke and air mixing. So if you're only really moving the air around but not getting it all the way through the catalyst bed. Use of platinum-based CO promoters. So platinum-based typically promote NOx formation. And then the use of antimony passivators often increase NOx as well. Here's just an idea without an additive, when you're regenerating the catalyst, what you typically see in regard to emissions. So you have hydrogen cyanide, then you have NO at higher temperatures. HCN's formed at low temperature, there's a second peak, and then there's an HCN to NO at higher temperatures. This is without a CO promoter in the spent catalyst. So this is a very complicated diagram because depending on how your regenerator is actually designed, you can take many of these paths. And it depends on your catalyst, it depends on the airflow, it depends on the general design of the regenerator. So you can form N2 when you destroy the hydrogen cyanide. You can form NOx. You can actually form ammonia, which then would potentially go to NOx. So there's a lot of reaction paths, and it depends on the regenerator itself and its design. So typically, platinum CO promoters oxidize hydrogen cyanide and ammonia mainly to NOx. So it does a good job of getting rid of the hydrogen cyanide and the ammonia, but it mainly goes to NOx. Non-platinum promoters actually oxidize mainly into N2 as opposed to NOx. So where NOx is going to be higher, typically a non-platinum based combustion promoter would be used. There's some other things here that are just a minor piece of things. I will say that I am not an expert on FCC additives, but my co-author is. I should be able to answer your questions on engines, certainly, but if the FCC additives portion brings up some questions, I'd be more than happy to either answer them or jot them down and get an answer for you. So, any questions, comments? The question is the EKG load on that drilling rig because they're laying pipe? Yeah, they're tripping in is what they call it. So they're laying the pipe in, and they they're fitting the new piece. Maybe they hit a hard spot, so that's when they're tripping in. It's a very high load swing process. Question is for compression and other processes, are the load swings the same as drilling, or are they more steady? They're more steady. Drilling is by far the most challenging to follow. Gas compression in general is a steady state process. So they don't do a lot of huge load swings. What is the applicability? The question is, what's the applicability of SCR in this third bullet point in the oil and gas industry? Drilling, certainly applicable. It is a bit challenging, but Wyoming required it along with the BLM, and it's been demonstrated to be a technology that can be implemented. Compression, certainly possible. We're seeing a lot in Marcellus right now up in Pennsylvania. This case study that I showed actually is kind of the bellwether for Pennsylvania to kind of look at, can we do this, and what is the backed that we think is going to be required. The real challenge is transmission engines. And some compression engines that run these low speed, old Cooper Bessemer, you pick the name. The temperatures of the exhaust fluctuate, but they tend to run in a very low range. We like to see around 575 F to inject urea. Quite often they don't make it to 500 or 550. So the options there are somewhat limited in that we need to either put a burner in, which has been done, or we need to look at ammonia, or we may be able to use urea with an enhanced maintenance schedule, because we do see big balls of urea form in the mixing duct if you don't pay careful attention. That drilling operation that I showed you on those diesel engines, they actually ran fairly low temperature. We inject urea at 500 F. They actually chose to do that against our wishes, but they had an enhanced maintenance schedule, and they had a sight glass right there in front of the injector so they could tell if there's a problem. So I would say transmission engines, these large slow speed engines are the biggest challenge to the SCR technology. Yes, sir. The question is the formation of formaldehyde from the methane emitted from the engine over the SCR. We haven't really found that to be the case in any of the work that we've done, but we also typically have an ammonia slip catalyst that we put behind the SCR. The ammonia slip catalyst has really a dual function. It's both an SCR catalyst and an oxidation catalyst. Can't tell you how it is, both, but it's designed to reduce, if that formaldehyde does form, it will reduce formaldehyde, other VOCs, and it also keeps the ammonia slip down to very low levels. But I have heard mention of formaldehyde formation over SCR, but I haven't really heard a big to-do about it. So.
It's pretty common, but still research is being done. Will that ammonia slip catalyst, will that take care of the CO also? The oxidation catalyst?
Will the ammonia slip catalyst take care of the CO also? Yes. In fact, the SCR system itself, if you go through from an engine into the SCR will actually incompletely oxidize hydrocarbons to CO. So you have a net increase of CO after the SCR catalyst. The ammonia slip catalyst makes up for that and then actually brings it to a positive reduction. So you might see negative 30% reduction after the SCR, but after the ammonia slip, you're at maybe 70% or 80% reduction. Any other questions? I know this isn't the whole oil and gas industry. Like I said, you don't want to see me up here for 8 hours. I don't want to be here for 8 hours either. No? Okay, thank you very much.